Hello everyone. Today I am presenting efficient SAM, leverage masked image pre-training for efficient segment anything. And to set the stage, we have to look at the segment anything model, which is also known as SAM. And this was one of the foundation for modern image segmentation. However, SAM has a massive deployment problem. And the image encoder VITH of SAM has nearly 632 million parameters. And this creates a high computation and memory cost that makes a real-time application nearly impossible. So if we compare SAM and efficient SAMs to other models, please look at the figure 1 of the paper. You can see that the original SAM, which is represented in this large circle, has very high average precision, but the throughput is very low. And other works like Mobile SAM and Fast SAM tried to solve this problem, but they often suffered a significant performance drop. Performance drop is very high. But the author of this paper proposes efficient SAMs. They maintain a very small performance gap from our foundation segment anything model, and the parameter size were reduced nearly 20 times smaller. A lighter model nearly 20 times by segment anything. So if we look at the core logic and the foundation logic of the SAM-I introduced in this paper is, this core innovation has a pre-training strategy called SAM-I. SAM leveraged masked image pre-training, SAM-I. To understand this, why this is special, we have to look at the standard masked autoencoders. In traditional masked autoencoders, these learns by reconstructing raw pixels. They tries to learn and reconstruct from the raw pixels, but the author of this paper argued that the pixels are very low target and doesn't capture enough meaning for complex segmentation. Instead, SAM-I teaches a small student model to reconstruct the latent features from SAM, and by reconstructing these high-level semantic embeddings, any tiny VIT backbone can inherit world view of the masking foundation model. Now look at the architectural detail of the paper. To get under the hood and look at the architecture, this entire framework is built on two stages strategy, stage 1 and stage 2. So stage 1 was the SAMI pre-trained logic. So the top half of the diagram illustrated the pre-training phase. So let's look in the more detail. The masking strategy. We take the input image and masked 75% of the pixels of the patches, and these are just random choices like the original MAEs. This high ratio prevents the model from cheating by simply looking at the neighbor pixels. Then comes the lightweight encoder. This is the master stroke here. So our only small portion is visible to the lightweight encoder, and this unmasked token is fed into our lightweight encoder. Its job is to extract the latent representation from these few visible fragments. So then comes the cross attention decoder. This is the major departure from standard ME. In our SMI decoder, the queries are masked tokens, while the keys and values are derived from both the unmasked embeddings and the masked tokens. Then the linear projection head. Because the output dimension of our tiny student model and the massive SAM teaches might not match, we use a simpler linear projection head to align them from comparison. So this is the stage 1. Then comes the stage 2. So let's first look at the heart of this paper, the maths behind this. So the brain of this learning procedure is now the stage 1 is over. Now look at the brain of this learning process, which is this reconstruction loss. So here we have used a L2 norm, and this FSAM is the gold standard, the feature embedding produced by the SAM-I's very massive VITH image encoder, and this FH is our student's best guess from the lightweight model's projection head. And the L2 norm is calculated Euclidean distance between these two. By minimizing this loss, we are essentially distilling the teacher's knowledge. We aren't teaching the student to see pixels. We are teaching it to replicate the internal logic, semantic understanding of a model, which is 20 times smaller than the original SAM. So now look at the stage 2 of the training. Now when the pre-training is finished, our SAM decoder is discarded and we take now the highly educated lightweight encoder and pair it with our SAM's prompt guided mask decoder. When we fine tune the entire system on the SA1B dataset, which is a collection of 11 million images and 1 billion masks, to transform it from a general feature extractor into specialized segmentation experts. Now we get our outputs, and let's look at the quantitative results from this paper. The results in this paper validate the feature reconstruction approach as a new benchmark. The zero-shot segmentation, efficient SAM achieves a 44.4 AP on the COCO dataset. For context, the original SAM has achieved 46.5 AP on this dataset, which is only a roughly a 2 AP performance drop down. But keeping in mind that the efficient SAM is nearly 20 times smaller than the original SAM. So yes, the performance gain, efficient SAMs outperforms the other fast model like mobile SAM and fast SAM by about 4 AP on COCO and LS both. And now looking at the generalizations, these SAMI pre-trained backbones don't just work for the SAM, they actually outperform standard MAE and DIETs across the image classification and object detection. Now let's just visually compare our results. Let's look at the quality of the output from all of the models and other works. Looking at the point and box prompts in figure 3 and figure 4, when clicking on the objects like horses, efficient SAM produces math nearly identical to original SAM. It captures the fine detail that fast SAM often misses. And in the figure 5, the segment everything in complex scenes like a tennis match, efficient SAM maintains a high level of objectness. It correctly identifies individual pairs and distinct scene elements where other lightweight models often merges them into one blob. Now we'll look at the contributions and the refinements which we have made on this paper. So we have fine-tuned the baseline model on a different dataset, which is ISET dataset, which is a collection of satellite images. So while the base efficient SAM model is general purpose powerhouse, satellite imagery presents unique challenges that standard dataset like COCO do not fully cover. And we are dealing with top-down perspective, varying atmospheric condition, extremely small or dense objects. And to bridge this gap, our first major contribution was fine-tuning this VITS backbone, specifically on the ISET datasets. So now look at the metrics. For quantitative analysis, the metric mean IOU has improved to 0.5361 from the baseline VITS model, which was 0.497. And similarly, the DICE score is also improved to 0.6579. And it was 0.5887 in VITS. And also the metrics like precision and recall are both metrics saw substantial climb, with precision reaching to 0.6912 and recall to 0.6986. And this balanced growth proved that our fine-tune didn't just make the model more aggressive at finding objects, but also more accurate in its the classification. Now look at some visual results. In the first visual, the baseline VITS achieves only 0.58 IOU score, but in our fine-tuned model it was 0.80, which was a massive jump. And in the second visual of detecting the very small objects, the VITS backbone has a IOU score of 0.47, and ours has a 0.81, which is again a significant improvement in our fine-tuned version. And at last, when we see the high density object detection, such as the parking in industrial areas, the baseline VITS is respectively 0.85 in detecting the dense objects, but ours also has pushed these results, the IO score, to 0.86. So by fine-tuning efficient SAM on ICER dataset, we have moved from a generalized model to a specialist with a domain-specific knowledge of satellite images. So we have successfully maintained the 20x speed of the efficient SAM architecture while significantly boosting the MOIU and F1 scores for the high-stake satellite analysis. So after fine-tuning our baseline model on the ICER dataset, let's discuss our proposed architectural changes in the mask decoder. So in our improved version, let's first discuss the original efficient mask SAM decoder. In a standard architecture, the process is linear. Image and prompt embedding pass through a two-way transformer incorporating self-attention and the cross-attention, and to create an output token. This token is then simply dot multiplied with an unsampled image embedding to produce the final mask. While efficient, this design often lacks special edge awareness to produce the final mask. Okay, so in our innovation, the proposed boundary aware decoder, let's see how it works. So first we have a shared dual head feature map. We take the transformer output and then treat it as a shared feature map, and then we had dual head branchings. The one is the mask head, which is pre-existing in our original efficient SAM model also. This continues to capture the coarse object regions. And then second, we have another head, boundary head, which is a lightweight CNN stack. It's like convolution, then batch norm, then ReLU, then convolution, and then sigmoid activation function. So this is a dedicated boundary map. And after this, we have used a Sobel driven supervision. During training, we have used a Sobel filtering process, like applying X and Y kernels to the ground truth boundaries directly from the mask. This provides the target signal that teaches the boundary head exactly where edge lies in our images. Then talking about the loss computation, to train this effectively, we implement a multitask loss function. So our total loss is the combination of both mask loss and the boundary loss. And by combining the standard mask loss, a new boundary loss, we force the network to not just classify pixels, but to precisely delineate where an object ends at the background begins. So let's see the results from this architectural change. So when we evaluate this on our cityscapes dataset, the metrics tell a very interesting story about the trade-offs. The trade-off were, you'll notice that the MOU and the MDI scores for our proposed model are slightly lower than the baseline model. So this is a known phenomenon when introducing high frequency edge constraints as the model become less forgiving of small pixel shift to a large region. So here's the reason for our accuracy or AP drop in our proposed model. But here we have some like the supporting points for our models. We have improved the boundary IU and the boundary F1 scores in our delta, like proposed baseline model. So while the boundary IOU improved from 0.4641 to 0.4802, and the boundary F1 improved from 0.6297 to 0.6452, which is a plus 0.115 delta. And the pixel accuracy was also improved from 0.6297 to 0.6452. So while the overall region based on IO dropped slightly, the boundary F1 and the boundary IO scores are significantly improved. This improves that our model is much more boundary aware. The model is boundary aware and capable of capturing the fine-grained special details that original efficient mask misses. So in conclusion, our architectural change is minimal in complexity but high in impact. While explicitly modeling boundaries through Sobel supervision, a dual head fusion, we have enhanced efficiency SAM ability to handle complex shapes and thin structures. This makes our version significantly more robust for real world scenarios like autonomous driving or urban planning, where edge precision is a safely requirement. So this is the our proposed architecture and the efficient SAM model. So thank you so much.